In section 9.8, we're going to look at power series. Now, specifically what we're going to be viewing in this section is we're going to think about how we can write a function as an infinite polynomial. Now, we just got done with writing functions and approximating them with polynomials of degree, 4s and 5s and 3s. That was approximating with Taylor polynomials. So we're going to look at how can a function be written as an infinite polynomial. So we can write a function, when I say infinite polynomial, something like 1 plus x squared over 2 factorial plus x to the third over 3 factorial, et cetera, et cetera, et cetera. Or g of x as 0 plus 1x plus 2x squared plus 3x to the third, et cetera, et cetera, et cetera. So if you think about infinite polynomials, we have this piece where it is coefficient times x to a power, another coefficient times x to a power, another coefficient times x to a power. So we can write a power series as an infinite sum of coefficients, which we're going to call a sub n, times x to the nth power. Now you can start your summation at 0. Most people will start their summation at 0 just so we have a constant term. And this is a power series, coefficient times x to various powers, and we let those powers go from 0 to infinity. And again, these coefficients vary by term. So this is a power series. Now this power series is centered at 0 because most times we think of polynomials like this, x to the fourth, but we saw in the last section that we actually can center at any place we'd like. So we can center this at c by replacing the x with an x minus c. So each x to the n is replaced with x minus c quantity to the power n. So that's a power series centered at c. Now, the big question of this section, is the convergence of power series. And obviously, it's going to depend heavily on the coefficients of what this power series is. So we're going to look at a bunch of different power series, and we're going to look at convergence. And then in the next couple of sections, we're going to say, or we're going to ask ourselves, well, how can I come up with a certain type of power series? Now, anytime we're talking about convergence of power series, we're going to have three options. Now, the first option, let's say the power series is centered at the number c. The first option is that the only place that the series converges is when x is equal to c. So, in other words, these coefficients over here, no matter what value you plug in for x, this series diverges. Does that make sense? Hopefully. So this power series really represents a bunch of different infinite series. And depending on what you plug in for x, this series could converge or not. And so what we're saying is that first case, no matter what value you plug in for x, as long as x is not c, this thing diverges. The only way this converges is when x is c. By the way, hopefully you notice when x is c, all of these terms become 0. So it's just an infinite sum of zeros. So that's our first option for convergence. We converge only when x is c. The other option for convergence is that the series converges no matter what value you plug in for x. So for all real numbers, you plug in a real number, and that infinite series, this infinite series here, converges no matter what number you plug in for x. Now, those two are the first two. The most interesting convergence option is that we converge within a interval. So exists a real number r, which is called the radius of convergence, such that the series converges when x and c are close to r, or I shouldn't say close to r, are x minus c are close to each other. So x minus c in terms of absolute values is less than r, and diverges when x minus c is greater than r, again, an absolute value. So this is essentially saying when x is close to c, it converges, and when x is far away from c, the infinite series diverges. Now, this convergence versus divergence, notice that in that last option, we said converges absolutely. So there's going to be a lot of ratio tests and things like that. But I want you to think back to the order of growth that we dealt with in 9.6 and before. We said, well, n to the nth power, that was sort of our fastest growth that we saw. N factorial was really fast. This b to the nth power, well, that was a fairly fast growth, again, as long as our base is greater than 1. N to the p power, where p is a constant, that's, again, fast growth, but it's not as fast as geometric, it's not as fast as factorial. And then things like natural log are still growing. And the other thing that you should notice here is that right here in the middle, we have b to the n. We have this geometric type growth. And if you think about this power series, well, what do we have here? X minus c to the n. So this x minus c is actually a base for a geometric growth. So that's going to come into play. So let's take a look at this power series and let's figure out what's going to happen based on looking at the power series. So I want you to push pause and think back to the order of growth and figure out which piece is going to be the most dominant one. So you should be well acquainted to say, no matter what you plug in for x here, it's going to be a real number. So you're going to get a real number. Let's just call that real number r to the n and n factorial. Now, whatever that real number happens to be, n factorial is a faster growth than geometric growth. So the n factorial is going to dominate, no matter what real number that is. So n factorial will dominate. It is in the numerator. No matter how you write this infinite series, it is in the numerator. Whoops. So the series will diverge as long as r is not 0. All right. So as long as this real number here is not 0, this thing is going to diverge because the n factorial will take over, and the n factorial is obviously in the numerator, and so there you go. Now, obviously there is an option for r to be 0 because our r was actually, we said x minus 2. So when we say as long as r is not equal to 0, basically what this option is we're saying as long as r is not equal to 0 is equivalent to saying as long as x is not 2. So this is the situation which converges when only x is 2 and diverges elsewhere. So converges when x is 2 and diverges for any other x. Okay, any other number you plug in for x. So I want you to use that same logic and push pause. Try to use that same logic on this example. So push pause, figure out where this thing converges. All right, so hopefully you went ahead and did that. So x plus 1 to the n, that's just going to be some real number. So you're going to plug in a real number here. We'll say r to the n, and then we have 3 to the n. Now, if you wanted to, you can rewrite this whole thing. I'm not going to do a whole lot of rewriting here. Whoops. But just in terms of rewriting this particular summation, again, think of it as going from 0 to infinity. I'm going to leave that off. This is like taking n divided by n factorial and then multiplying by a real number over 3 all to the n. R over 3 to the nth power. Hopefully you guys understand what I mean by there. I'm replacing this x plus 1 with an r. So we have a geometric piece, which is r over 3 to the nth power, some real number over 3 to the nth power. And then we have this linear piece, which is just n to the first power. And then we have an n factorial. Now, n factorial is the fastest growth around. And so it's going to dominate this whole thing, meaning whatever n factorial does, the whole series, n factorial is going to dominate the series. So since it is in the denominator and it's dominating everything else because it's the fastest growth around, no matter what r is, n factorial grows faster. Since the n factorial is in the denominator, this series is going to converge no matter what you plug in for your r or for your x. All right, so this is one where it converges everywhere. Meaning this is something that converges regardless of what you plug in for x. Let's go and look at example 3. Now, example 3 has x to the n over n, and we're starting at 1 going to infinity. Now, starting at 1 versus starting at 0, whoops, doesn't actually make any difference. But we have x to the n over n. So let's look at this. We have x to the n over n, and we're taking an infinite sum. So which part is going to dominate, the n to the first power or the x to the n? Well, this x to the n is going to be geometric. X to the n is geometric and has faster type growth than any sort of n to any power, which in this case, we're talking about n to the first power. So x to the n is going to dominate. And it'll dominate in the way we talked about in section 9.6. Like it's the main cause. So if x to the n is something that causes this summation to converge, then the whole thing will converge. If x to the n is something that causes this summation to diverge, then this summation will diverge. All right. In other words, this n to the first power might as well just be another number, okay? Now we know something about geometric series. For geometric series, if we have an infinite sum, let me write infinite sum of a r to the n, we know that this thing will converge when r is between -1 and +1. So basically, what I'm saying is that this a, this coefficient, even though in geometric this a is a fixed number, even here, the r to the n power, in this case, our r to the n is just x to the n, is going to converge when that geometric piece is between -1 and 1. So in our case, this infinite sum is going to converge when x is between -1 and 1. All right. And this gives you your interval of convergence that I was talking about. So it converges when x is between -1 and 1. That's called the interval of convergence. Okay. By the way, the radius of convergence would be 1 because this is centered at 0 and we go from 1 unit to the right, 1 unit to the left from 0. So radius of convergence is 1. Interval of convergence is from -1 to 1. All right. So radius of convergence is 1. Interval of convergence is from -1 to 1. Okay. Now, by the way, there is something that could and could not happen. And this is a great example of what could and could not happen. The geometric series says it converges when r is between -1 and 1. That'll work whenever a is a fixed number. When a is a fixed number, it also diverges when the absolute value of r is equal to or greater than 1. Now, in our case, we don't have a fixed number as a coefficient. If I were to rewrite this, this would be like 1 over n times x to the n. So we don't have a fixed number as a coefficient. And so what we are going to have to worry about is at -1 and at 1, does this sum converge? In other words, does it also converge at the endpoints? By the way, it's never going to converge at more than 1. It's never going to converge at less than 1, but it could converge at the endpoints. So we do sometimes check the endpoints for convergence. So at the endpoints, let's say we plugged in x as -1. If we plugged in x is -1 at the endpoint here, excuse me, x is -1 into our series. Well, this is an infinite sum, -1 to the n over n. That's an alternating series. The underlying limit, that's limit of 1 over n. Let me just write limit of 1 over n. This is obviously limit as n goes to infinity of 1 over n is decreasing towards 0, and therefore at x equals 1, or excuse me, x equals -1, this series converges. all right? When x is equal to positive 1, however, well, what do we get? Whoops. Let's look at the series when x is equal to positive 1. When x is equal to positive 1, this is just 1 to the nth. That's always going to just be a positive 1 over n. And this is a p-series test. Where we're taking n to the first power, so p is equal to 1. And so this series diverges at the x equals 1 endpoint. So when you plug in a positive 1, this series diverges. All right. So that's kind of what happens with this interval of convergence. Sometimes both sides, if you plug in 1, plug in -1, they both diverge. Sometimes you plug in 1 and -1, they both converge. Sometimes, like this time, you plug in 1 and -1, and one diverges and one converges. But again, the main part is that the geometric piece dominates because it has faster growth. So you can plug in anything from -1 to +1 in for x. So let's take a look at another one where we don't have just x to the n as our geometric piece. What if we have something like this, where we have x minus 2 to the n, but we also have a 3 to the n in the denominator. So we're going to take an infinite sum as n from 0 to infinity goes, x minus 2 to the n over 3 to the n. I want you to push pause and think through this if you can. So let's do this. X minus 2 to the n over 3 to the n. Now, the easy way to deal with this is to create one number that you're raising to the nth power. That number will be x minus 2 over 3. So that really is your r. You're taking an r in the geometric sense, and you're leaving that r as x minus 2 over 3 to the nth power. By the way, this works exactly like the geometric series because our coefficient out front is an implied 1. So we don't, or a is 1 with the geometric series. So we know, based on geometric series, that this converges when this r is between -1 and 1, which means that this thing will converge when x minus 2 over 3 is between -1 and 1. All right. Now, hopefully you know how to solve this. You'd multiply all three sides by the number 3. So you get -3 less than x minus 2 less than +3. And then you'd add 2 to all three sides. If you add 2 to the left, you'd end up with -1. If you add 2 to the middle, you end up with x. And if you add 2 to the right-hand side, you'd end up with a 5. Okay? So by the way, that is the interval of convergence. Of convergence is when x is between -1 and 5. Sometimes I write the interval as x between -1 and 5. Other times people write the interval like I did in the last problem where they put the, where they put the lowest number. It's almost like an ordered pair, lowest number, comma, highest number inside of parentheses. Okay. So on the test, I'll just say interval of convergence is when x is between this number and that number. By the way, in this case, if you check the endpoints, if you plug in x as -1, what's this summation come out to? Well, this summation will come out to, well, think about what happens when x is -1. So we get -3 to the n over 3 to the n. The 3's will cancel out and you'll be left with -1 to the nth power. So what you're getting is -1 to the nth power, excuse me. And by that, by geometric series, we know this diverges. All right, that series diverges. By the way, if x is equal to a +1, then what's going to happen on this series? Did I say +1? If x is going to be 5, I'm sorry, got to go to the endpoints. I was looking back there. Got to go to the endpoints of my interval of convergence, so -1 and 5 in this case. So if x is equal to 5, you get 5 minus 2, so you get 3 to the n over 3 to the n. That's always going to be a 1, so that's going to be an infinite sum of just positive 1s. And by the way, that also diverges based on either the geometric series test or the fact that the underlying sequence never goes to 0. So notice that in this case, both endpoints, when you plug them in, cause the series to diverge. Okay. By the way, if you're looking at the radius of convergence this time, going from -6, well, we're centered at 2, so going from -1 up to 2 is a jump of 3. Going from centered at 2 to 5, that's a jump of 3. So technically the radius of convergence is 3. Okay. By the way, if you take the distance of your interval of convergence, the lowest and highest, you can see that's a distance between 5 and -1 is 6. Half of that is the radius of convergence. So you're always going to get that. But I always think centered at 2, if we're centered at 2, how far do you have to go to get to one end? How far do you have to go to get to the other end? So that's your radius of convergence. Radius of convergence, in this case, is 3. All right, I want you to try the next one all on your own. So take a look at example 5 and decide what the radius of convergence and the interval of convergence is on this one. And if you want, check out those endpoints too. Okay, hopefully you had a chance to do that. So x plus 3 to the n over n to the third summed up from 1 to infinity. Well, we have an n to the p versus a geometric piece or an exponential piece. The exponential piece is going to dominate. And so this exponential piece dominates. Geometric series says as long as this exponential piece has base, which is between -1 and 1, we're going to converge. So this exponential piece, x plus 3 to the n, that base is x plus 3. So we put that between -1 and 1. By the way, x plus 3, this means that the series or the power series is centered at -3, right? And so anyways, we're going to subtract 3 from all 3 sides. Subtract 3 from the left, you get -4. Subtract 3 from the middle, you get x. And subtract 3 from the right-hand side, you end up with -2. And that's your interval of convergence. The interval of convergence is from -4 to -2. The radius of convergence is 1 because we're centered at -3, and you got to move 1 to the left or 1 to the right to get to the endpoint of your interval of convergence. Now, when you look at the endpoints and whether the series converges at the endpoints, I'm going to do this by hand. Plug in -4 first. -4 plus 3. It actually doesn't matter which one you plug in first, but you plug in -4 into the x. You end up with -1 to the nth power over n to the third by the alternating series test. This thing has to converge. I'm not going to go through the whole thing. But this series converges because of the alternating series test. 1 over n to the third decreases to 0. Now, similarly, down here, we're going to plug in -2. If you plug in -2, and then for x, -2 plus 3 is a 1. 1 to the nth power, that's really just 1 every time. So we get 1 over n to the third. Now, that's a p-series test. Whoops. P-series test. In this case, p is 3. So because p is 3, this series converges as well. So in this case, the power series converges at both of my endpoints. All right. So some people would go up and change this from a less than to a less than or equal to, or less than to less than or equal to up here. I'm not going to require you to do that. I just want you to understand that sometimes both of these endpoints, when you plug them in, the series will converge. Sometimes, like we saw in our last problem, at both of the endpoints, the series diverged. And sometimes, like in the problem before this, one converged and one diverged. So there you go. That's how we find the interval of convergence and the radius of convergence once I have a power series. Now, I want you to try one more of these on your own. Find the radius of convergence and interval of convergence for the following power series. Infinite sum of 5n squared times x minus 4 to the nth power over 7 to the nth power. You push pause on the video and did that. So 5n squared x minus 4 to the nth power over 7 to the nth power. Now, we're going to combine all of our geometric parts, x minus 4 over 7 to the n, and we're going to see that versus a polynomial, the geometric or the exponential growth will dominate. So whenever this converges, whenever the geometric piece converges, the infinite series will too. So whenever r is between -1 and 1, this thing is going to convert, or excuse me, this series will converge. And in our case, the r is x minus 4 over 7. If you multiply both sides by 7, you get -7 in between x minus 4 and +7. Or excuse me, x minus 4 is between -7 and +7. Add 4 to all three sides, you get -3 is less than x is less than 11. Now the interval of convergence is from -3 to 11. The radius of convergence is obviously 7. We're centered at 4 here. Our power series is centered at 4. So centered at 4, move up to 11, that's a 7 unit jump. Centered at 4, move down to -3, that's a jump of 7 units. So radius is 7. Now at these two endpoints, -3 and 11, well, at -3 and 11, if you plug in -3, -3 minus 4 is -7 to the n, so you get -7 to the n over 7 to the n. That's -1 to the n, and then 5n squared. Now, obviously, this is an alternating series, but this 5n squared If I take the limit as n goes to infinity, it does not go to 0. In fact, it goes to infinity. Therefore, this series diverges. If you plugged in 11, we have 5n squared. This, excuse me, 11 minus 4 is 7, so you get 7 to the nth power divided by 7. 5n squared is what's remaining after the 7 to the nth powers cancel each other out. And an infinite sum, this 5n squared never goes to 0, so this infinite series diverges. So these two endpoints both lead to series diverging, but still, again, the radius of convergence is 7. The interval of convergence is between -3 and 11. Now, I'm going to make an observation here. I think you kind of get the point of this section. You can do more and more and more stuff. By the way, there's more and more tricks as well to look at convergence and where things converge. I'm not going to dive too much into the details right now in terms of the algebraic manipulation, but I do want to give you one tool that you can work with as far as the algebraic manipulation goes. So here's an interesting fact. If we have a power series, let's say it's centered at 0. So we'll call that power series f of x. So this function is a power series centered at 0. What would happen if I took the derivative of f of x? Well, based on derivative rules, I could take the derivative of each component, each term here. The n would come down front, you'd get a to the n times n, then you get x, and you lower your power by 1, okay? Now, actually, the a sub 0 term would have gone away. Let me fix that real quick. There we go. So I just changed the count from a 0 to a 1 because when you're at a0, that a0 term will just go away. So you might as well leave it off when you take the derivative. But n goes out down, every other term, n goes down in front, multiplies by a to the a sub n, x to the lower your power by 1. By the way, notice that when you multiply by n, multiplying by n does not change what the fastest growth around here is because we already have an exponential or a geometric growth laying around here. So multiplying by another n doesn't change which type of growth dominates. The same thing or a similar observation can be made when we integrate this function. So I still have that same function, it's polynomial function. If you integrate using the properties of integration, well, we know that each term can be integrated by adding 1 to the exponent, so you get x to the n plus 1 in the arbitrary term, and then dividing that coefficient by an n plus 1. This one we do need to start at 0 still. And in fact, we also have to add a plus c when we integrate, right? But again, dividing by n plus 1 doesn't actually change what's the fastest growth around. The fastest growth around, we already have a exponential or geometric growth. Dividing by n plus 1 doesn't change the fastest growth that's here. So what I'm trying to get at is this observation. If f of x is a power series, then it is going to have the exact same interval of convergence as its derivative and as the antiderivative of the function. So when you integrate the function or when you take a derivative of the function, you are going to get the exact same interval of convergence. Now, I say exact same. I should do one little asterisk. It's exactly the same except maybe not at the endpoints. That multiplying by n or dividing by n plus 1 could change the convergence at the endpoints. So that's kind of a nice trick that you can deal with. So maybe you don't know a power series for f of x, but maybe you know the power series for the antiderivative of f of x. Or maybe you don't know the power series for f of x, but you know the power series for the derivative. And you can still figure out what the interval of convergence is. Just again, maybe it could be slightly different at those endpoints. So we already found the interval of convergence for this one earlier. If you remember, the interval of convergence went from -1 to 1. So x between -1 and 1. And at the endpoints, the -1 converged, but the +1 diverged. Well, if we were going to multiply by an n here, if we're going to take the derivative, the interval of convergence would still be from -1 to 1, but it turns out that both endpoints would diverge. And if we did the antiderivative of f of x, we're going to have the same interval of convergence, again from -1 to 1, but at both endpoints, it turns out the antiderivative diverges, or to me, converges. I apologize. All right, so let me write down what I just said. So we have a function here. Earlier we saw that it converges when x is between -1 and 1. And earlier we saw that at this endpoint, when you plug in 1, the series diverged. But when you plugged in -1, the series converged. So what I'm saying is that if I would have taken the derivative of this function, by the way, derivative of this function would look like this. N comes down, you multiply, cancels out this n, and you just get x to the n minus 1. Well, it still is going to converge on that same interval from -1 to 1, except in this case, when you plug in a 1, the series diverges, and also when you plug in -1, the series also diverges. And by the way, you could have also taken the antiderivative. The antiderivative, it turns out, add 1 to the exponent, new exponent's n plus 1. You divide by n plus 1, so you'd get n squared plus n in the denominator when you multiply that out. This plus c won't matter a lot. But you take the antiderivative of f of x, again, it still has the same interval of convergence, but in this case, when you plug in 1, the series converges, and when you plug in -1, the series also converges. So the point is saying that it converges on the exact same interval, except maybe the endpoints are going to be different. All right, so the f of x, the derivative, and the antiderivative will all have convergence on the same interval. And by the way, that's also for the ones that we did way at the beginning with the n factorial. Multiplying by n is not going to change whether n factorial dominates or not. So multiplying by um, n factorial still dominates. This one is still going to converge everywhere. Multiplying by n, again, not going to change, the n factorial dominating. This one is going to converge only when you plug in the number 2. And so that is what section 9.8 is all about.